today. Let me briefly introduce him. So he's a high energy theorist. And well, he did his PhD at CBPF in Rio. Then a couple of postdocs in IFT in São Paulo. Also another one at the University of Massachusetts. And from 2014 to 2024, he was a professor at the Universidade Federal Rural do Rio de Janeiro. And last year, he became a professor at the University of São Paulo. So he works with scattering amplitudes in gauge theories in gravity, as the title says. But he also works with quantum and classical gravity and early universe cosmology. So it's a pleasure to have him here today to tell us a little bit more about his work. And so, Gabriel, thank you for being here, and the stage is yours.
Thank you, Marcia, for the kind introduction, and thank you, and Dimitri, for the invitation. I'm happy to be here and to talk a little bit about the things that I've been doing myself and with some collaborators. And well, if I have to commit myself with the topics that we are going to discuss here today, these are the ones. So the idea is just trying to give a general picture of those tools that we use nowadays in many branches of physics concerning these modern amplitude methods. And throughout the course of the seminar, I'm going to be more specific in what I mean by modern amplitude methods. And then in the end, we're going to look into some cool applications that you can do with those methods. And of course, I'll be biased, so I'm going to talk about the applications that I'm doing right now, but there are some near future perspectives in other branches, and I'll be happy to discuss with anyone who's kind of interested. And okay, guys, so fasten your seatbelt. Hope you guys are not hungry, because we'll be talking about a lot of things today here. So okay, so as we all know, scattering experiments have been really fundamental for us in order to try to understand, let's say, the fundamental blocks of nature. And I think the most incredible example is given by the Standard Model. As we know, the Standard Model was built upon many of the scattering data throughout many decades, right? And the primary object that we are interested in, once we talk about scattering experiments, is the so-called scattering cross-section, or the differential cross-section. And simply put, this quantity incorporates the probability of a given process to take place as a function of energy and momenta and possibly spin of the particles involved, right? And the interpretation that we find from data that we take from these scattering experiments, it's based on a given theoretical framework, which traditionally is quantum field theory, right? But actually, in quantum field theory, there is an object that we calculate before the differential cross-section, which is the scattering amplitude. So roughly speaking, the cross-section is just the absolute value square of a given scattering amplitude. And then even though the cross-section is itself the observable associated with this, with such experiments, we usually say that the scattering amplitude is the observable that we are interested in. Okay, so this has been a long story, and I'm not putting the researchers associated with the old story from the 60s, the famous S-matrix program, right? But every now and then here in this talk, I will mention this part of the program, because it has some, you can say that today we understand better the things that we were trying to understand back in the 60s. But those guys, what I call early explorers here, are guys from late 80s and beginning of the 90s. So at that time, there was a lot of particle phenomenology involved, because traditionally speaking, that's where the most part of all the applications of these methods were headed to. But nowadays, if we have to put simple words to describe the efficiency and the importance of those methods, we would say that this is for the development of more efficient ways to calculate those scattering amplitudes, right? And of course, there are many other things that I could discuss, but I won't have time. There is, which are associated with the mathematical structure associated with those scattering amplitudes, such as things that we call polytopes, amplitude hadrons, associated hadrons, etc. Right? So the idea is to envisage the amplitude as the volume of a given abstract mathematical space in very generic words, right? But we can elaborate this more. So nowadays, we live on years that we develop something that you can call amplitude bootstrap, which has some similarities with something that you might have heard, which goes by the name of conformal bootstrap. So traditionally, what we do, we start with Lagrangians, and from the Lagrangians, we extract the Feynman rules, and from the Feynman rules, we start to put up the Feynman diagrams to calculate a given amplitude, right? So now the idea is try to consider from the scratch your physical observable, which is the amplitude. And then we impose constraints, such as symmetries that you expect for the particle spectrum to obey, or any mathematical relations that you assume that those guys should satisfy. And then you check whether you can write the most general amplitude given your particle content. And then maybe you will find something that has some logical sense. And then, of course, then it comes physics. Physics will, as we will see, physics enters most basically in which ways that you impose the analytic structure of those amplitudes. That's where physics actually enters. Okay, so more formally, what is a scattering amplitude? So consider a given reaction with particle 1 plus particle 2 on a collision process, generating particle 3 plus particle 4, etc., etc. So each process here, right, such as this one, such as this one, will be characterized by the types of particles that you are considering it. So you can imagine the scattering amplitude as a map, right, where the data that you insert are the data associated with the particle. So the energy, the momentum, the type could be, for instance, you can use the spin to label the type of the particle, and then it gives a number, typically a complex number, quantum mechanics, right? And then you impose constraints. The two most important constraints that we input is the on-shell condition. So we'll assume that the external particles obey the relativistic on-shell condition. It's not necessarily, of course, but most of the time here I'll be talking about on-shell scattering amplitudes. But assuming that you want to calculate off-shell quantities such as correlation functions or form factors, you can relax this condition. But anyway, so I'll be assuming that our amplitudes, the external particles that you are scattering, that this quantity is describing, they obey the on-shell condition. And the other one constraint that is important is the conservation of form momentum. So, and here I'm writing in a given incoming momentum convention, but you can distinguish between incoming and outgoing particles very easily from here. So, so these are the two constraints that you put on your amplitude. Okay, so this is the first, let's say, abstract step. And then you ask yourself, okay, but how do I calculate this? So traditionally, we come up with a set of parameters, and then we assume that those parameters are small, whatever it means. And then if you have this set of parameters that are small in a given sense, you can envisage a kind of a power series expansion around those parameters. So basically, that's what you do. And then, of course, you can do the whole computation using just algebraic manipulations, etc. But this guy, Feynman, someone said, he brought quantum field theory to the masses. So he saw that in the course of this calculation using this tool, perturbation theory, all terms, they organize themselves as kind of diagrams that you can sum up, and those diagrams, they obey some very specific rules, which came to be known as Feynman rules. And for each of those objects, for each of those things that you draw on a given diagram, you associate a given formula. And then you put up everything together, and then you have a formula for each one of those diagrams, right? So here I'm being very sketchy, because for each of the perturbation theory, which you call true level, one loop, two loop, etc., you have many Feynman diagrams. So this is just a representative of a true level diagram, but you must imagine that you have many other contributions at this order, and then at this order, and then at this order, etc., And then you sum up everything, and then you have the scattering amplitude that you want to achieve, the result that you want to achieve. Actually, more formally, right? You can imagine the whole process as an operation that will map a given initial state to a given final state, right? And each of those states are something that we call single particle states, right? In your asymptotic spectrum. So your scattering matrix, right, is the guy that it's a unitary operator, quantum mechanics rules, and it is the guy that will do this map, that will perform this map, right? So traditionally, what we do is to write the S matrix, as we call this guy here, in this way, right? To separate between the things that we are interested in from the things that maybe we are not that interested in. And then the thing that we are really interested in is the T, the transfer matrix. And then the scattering amplitude that you calculate using Feynman diagrams, Feynman rules, is the matrix elements of this transfer matrix. That's the guy that you calculate. So in 5 minutes, I'm giving just the overall picture of what we usually do in quantum field theory if you want to calculate a given scattering matrix, right? But then the question is, the Feynman diagrams are really cool for you to understand the physical picture, to understand what is going on in a given scattering event or in a given processes, whatever is the branch that you are discussing, be it in particle physics, where is traditionally more suited to, but in condensed matter physics as well, you will see people talking about Feynman diagrams, but not necessarily. If you want to really have a computation, not necessarily the Feynman diagrams will be the most useful object for you to consider. And a textbook example is given by gluon scattering at tree level in quantum chromodynamics, or if you prefer, just Young-Mills in a given SUN theory, non-abelian gauge theory. So start with 4-point scattering. So 2 gluons in the initial state and 2 gluons in the fourth state. And then you have just 4 diagrams using Mandelstam variables, just S, T, U, plus a contact diagram. And then for diagrams, you can calculate by hand. That's not that difficult. Just a couple of pages, and that's it. And then you feel happy. Okay, then you feel happy, and then you try to increase with 1 more gluon in the final state. It could be at the initial state, but whatever. Then you find that to describe completely this amplitude, this process, you need to calculate 25 Feynman diagrams, which is not as bad as it seems. You still can calculate by hand more than a couple of pages, but you know, you are an adventurous guy, you feel good about it, and then you go to 6 gluons. Well, 6 gluons, now you need 220 diagrams, right? So that's not something that you want to spend your weekend doing, so you probably want to use very good mathematical codes or any software that you like to have at least on a couple of days the result associated with 6 points gluons in your scattering experiment, right? And in your scattering amplitude. But then, as you can easily see, each gluon that we put in any of the sides of the reaction, the number of the Feynman diagrams that you need to calculate exponentially increases, right? Well, something that you can impress somebody that is discussing with you physics in the bar, this number of Feynman diagrams, they grow as something that we call the Catalan number. So it's silly, but you know, it can be impressive for somebody who likes to know a little bit of number theory. But then you see, consider a process that you have 10 gluons. Then you need more than 1 million diagrams. And then it's easy to see that even if you have the fastest computer, you have the quantum computer that does everything that you can imagine, at some point, this thing will increase complexity in such a way that it's almost impossible to give you, in a timely manner, right, before the universe collapses, the answer for your question. What is the scattering amplitude associated with any particle gluon scattering? But then, if you come up with a way to calculate all those diagrams, and then you take everything, and then you square to obtain the associated cross-section, you will see that the result is damn simple. As simple as writing, I don't know, in one line. So, for instance, if you consider a process, so this is just an example, what I was saying. If you want to calculate a brute force calculation, so if you want to use a brute force calculation for the 5 gluons, so that's, whoops, that's this guy. Oops. So this guy, 5 diagrams. Oops, here. So this guy. So you have to calculate this, right? So many of the terms here, right, are made by Lorentz invariant combinations of momenta and the polarization vectors of the gluons, right? Basically, this is because you want to keep up with gauge invariance of your result. So it's a kind of redundancy that if you're using the field description, the Feynman diagram description, this is something that you have to use. But as I said, if you take everything there, and this is just a part of the calculation, right? So multiply this by 5, and then you take everything square, and then you find a very cute and simple result. So for instance, if you consider any gluon scattering with this helicity configuration, you will find this result. So as I said, it's really, really, really simple. So this amplitude has a cute name, which we call MHV, or maximum helicity violating amplitude, but whatever it means. But what's lying behind here, the simplicity of this result, is the usage of other variables to describe your scattering experiment, or your scattering amplitude. And in this case, this is so-called spinor helicity formalism. Well, it's pretty much the same when you are an undergrad, and then you are told to calculate the electric field, the static electric field, outside of a uniform charged sphere. And you are not using the Gauss law. And then you're just using Coulomb's law to calculate the electric field outside this uniform charged sphere. You can use Cartesian coordinates. Yes, of course. You can do whatever you want. But you're going to spend a hell to do the computation. And then you find that the computation is so simple, right, that you're missing something. And what is the thing that you're missing? The good variables to describe your system. Variables that match suitably the symmetries that are associated with the system that you are calculating, in this case, the electric field. So in this simple case, if you use spherical coordinates, the calculation is really easy. Not easier than, of course, the Gauss law, but this is something else. But it's easier, right? So you find, okay, so if I use the correct variables adapted or more adapted to the symmetries of my problem, maybe I will streamline the computation. So this is the kind of thing that happens here, right? So basically, these variables here that we call the spin or helicities, they are most suitable to describe massless scattering. They streamline your computations. The computations are very more compact if you, in comparison with the usual computations using momentum space amplitudes, right? And then, of course, this has to do with Lorentz representation of momenta. Actually, have any 4-vector, right? And then you can always write them using this kind of contraction with sigma matrices. And this is if you are using a particle which is massless, this determinant gives you 0. So the determinant of this equals p squared. So this is 0 if you are dealing with massless particles. So a 2x2 matrix which has 0 determinant, Vanich determinant, is a rank 1 matrix. So you can always write as a direct product of 2 vectors, just linear algebra, right? So these are the spin or helicity guys that I was mentioning. And then the symmetry that they make more manifest, which makes the calculations more compact and more easy to perform, is the little group. We always talk about fields, but fields transform as a given Lorentz representation. But we don't scatter fields, we scatter particles, right? And particles transform under the little group. So this ambiguity of fields is the thing that it lies behind. You have this, this kind of monster to do the computation, right? So if you just use those variables for massless scatterings, then you see that your expressions are much more handleable. And then you can perform this calculation by hand in just a couple of minutes if you are smart enough. So this is one of the ingredients that is really important nowadays to do this kind of computations. And even if you have massive particles, you still have a generalization of this formalism, which not necessarily generates more compact expressions, but at least it gives you a unified formalism to try to attempt to take all kinds of particles of any masses and any spins in a given single formalism instead of, for massless particles I use this formalism, for massive particles I use another. So you unify all formalism in a given way, right? Well, another ingredient which is important for us, especially if you want to calculate loop level amplitudes, is the famous generalized unitarity method, which roughly speaking uses the unitarity of S matrix, or the generalized optical theorem, to calculate loop level amplitudes from the knowledge of lower level amplitudes. And this is the point where we really made some progress concerning what we were doing back in the 60s. So what was the program back in the 60s? After the papers by Landau and collaborators, right, stating that quantum field theory may not be very accurate to describe physical process, because at some point we'll give you meaningless results, right? People start to focus on the observables, which by then, remember, we were in the 60s, so we were drowning on experimental data coming from experimental scattering experiments. So people start to focus on the observable, the scattering amplitude. So the S matrix program was born, or at least was born in the way that we understand today. So the general picture was given. Let's say I want to know a given function. If I know everything that is to know about its analytic structure, can I reconstruct this function? So basically, simply put, this was the aim of this program. And as you can see, it's really ambitious because it was very generic. Oh, give me a function, give me everything that is to know about the analytic structure of this function, branch cuts, poles, etc. And then I can reconstruct this function, right? So of course, it was doomed to not work. But then the point is, we don't actually need to know this for any kind of function mathematics. We need to know this for a specific set of functions, Feynman integrals. So if we know about the analytic structure of those Feynman integrals, then we can reconstruct the amplitude. Then this is the generic idea of the generalized optical, a generalized unitarity method. So usually we learn in textbooks that if we want to prove this formula here, right? Oops. If we want to prove this formula here, we use something that we call the cutting rules. And the cutting rules are something that you take two internal lines of a given Feynman diagram, and then you cut. Cut means you're going to put the propagators, the associated propagators on shell. Put the propagators on shell means you're going to replace the propagators by delta functions, on shell delta functions in this way, right? And then, but this is textbook. Once you do this, right, you are exploring a kind of analytic structure of your amplitude. In this specific case, the integrant of the amplitude, so the unintegrated amplitude. But you can explore another singularities. You can explore further analytic structures of your amplitudes. And by that, you would cut more internal lines. And then when you do that, when you put more and more propagators, and you have, of course, an upper bound, depending on the loop level and the dimensions, once you put more and more propagators on shell, right, you are going to explore more and more of these analytic structures behind your unintegrated amplitude. So the idea is do that, which amounts, in a given sense, to calculate residues, right? Because even though we are talking generic about loop amplitudes, the integrand are just rational functions, right? So we are just integrating rational functions, which of course, as you integrate, are going to generate everything sophisticated that you can do, that you can use talking about complex variables such as branch cuts, etc. But they are just rational functions. So presumably, you know what lies behind the analytic structure. And that's exactly where physics enters. Physics fixes the kind of analytic structure that you expect from those guys. For instance, if you are talking about a tree-level amplitude, you are talking about an exchanger of a particle, right? So this is a pole. So if you are talking about the threshold of production of particles, now you're talking about a branch cut. So for each, let's say, for each feature that you expect in your given scattering experiment, production of particles, resonances, exchange of particles, you have a kind of analytic structure that you can impose in your amplitude. Or at least you expect this amplitude to have. And then you explore this using this more than two cuts in your Feynman diagram. Then you can use this idea to calculate residues, which actually I didn't need to put in quotes. They're actually residues. But what you are doing are just calculating products of three amplitudes. And then you can use this to calculate one loop, level amplitudes, two loops, three loops, etc., etc. So that's basically the idea behind this method. And it's been really useful, right? Especially in situations where you know what is the basis in which you are expanding your set of integral Feynman integrals, right? At one loop, you know, at one loop, any one loop amplitude can be expanded in terms of this scalar integral. So this is a scalar box integral. This is a triangle. This is a bubble. Possibly tadpoles, etc., etc. So At 2 loops and 3 loops, things are more subtle. Then you have to use other techniques, which I'm not going to be able, due to time constraints, to talk about this. But everything goes by the names of IBPs, integration by parts techniques, in order to find this set of master integrals which you can use as a basis to expand your Feynman integrals. And then after you do this, these coefficients are found using the unitarity method. So that's basically the idea, right? Okay, so this is one important ingredient for any kind of process that you can imagine. But now, let's focus even more our topics here. So instead of talking about any kind of particles that we could do using that we can deal with using the generalized unitarity method, let's assume now that we are talking about massless spin-1 guys, or theories involving massless spin-1 guys, especially gluons, but you can talk about also photons and gravitons, right? So these two ingredients, right? Color-kinematics, duality, and double copy, they are important for us to describe those guys, especially the double copy, right? But the double copy comes from the color-kinematics duality. So simply put, the use of those tools lead us to the famous slogan in which you can envisage gravity as gauge theory square. So in a given sense, you can expect this from the knowledge of your particle spectrum. There are some caveats, I'm going to discuss this, but so it's like, imagine that if you put two gluons together, you get a graviton. Quote, but that's the idea. And it doesn't, this thing, the first incarnation didn't come from quantum field theory, but it actually came from those gentlemen here, Kawai Liu and Tai, studying amplitudes and string theory, right? So, but to have the double copy, as we know from quantum field theory, you need this ingredient, color kinematics duality, which is a duality concerning the color factors of your Young-Mills amplitudes. Remember, it's a non-abelian gauge theory, so when you calculate the amplitudes, there's going to be necessarily factors concerning the algebra associated with this non-abelian gauge theory, which by that I mean structure functions, matrices associated with the given representation of the gauge group, etc., etc. So you have to have these color factors. We generally call this generic color factors. And then you have numerators. These numerators, they codify the Lorentz invariance of your amplitude. Lorentz invariance imposes that those guys must be expressed as invariant scalar products between the momenta of your external particles and polarization vectors. So basically you have these two ingredients, color factors and numerators. And then if it is possible, and it is, you can prove at any given multiplicity level at tree level. And if you have a representation in which your numerators obey the same algebraic relations of your color factors, then boom, you have the color kinematics duality. So let's see generically how you can come up with this. So imagine that you have a very generic gluon amplitude, right? So with a given number of external gluons. So very sketchy, the mathematical formula associated with a given Feynman diagram, in which I'm just considering the cubic vertices. I can elaborate more why I'm not considering the quartic vertices, but the idea is that you can always write the quartic vertices as cubic vertices. You can always collapse using contact diagrams, and you can put everything together here in the numerator factor. So basically what you only have is just trivalent vertices here. So generically speaking, the mathematical formula behind this is this guy. So inverse propagators, the numerators I was mentioning, and the color factors, right? So the color factors, right? They're algebra, so they obey specific algebraic relations, such as Jacobi relations, right? You would expect this from the algebra. So, but then, if you use the fact that they obey these Jacobi relations, you can always deform the numerators in such a way that your amplitude stays the same. And so you see, I'm taking three generic Feynman diagrams in which they kind of have relations resembling the Mandelstam variables in a 4-point scattering. This is not on purpose, because that's exactly where you would find numerators in which you can deform and use this, let's say, more generic form of the Jacobi relations to prove that the amplitude stays the same. So it's a kind of a gauge invariance, right? So generically, if you calculate these numerators using traditional Feynman rules, these numerators are not gauge invariant. But there is always a way that you can deform them to put in a given representation in which they will obey the same algebraic relations as the color factors. And then this is the color kinematics duality. And then you can prove that they establish further linear relations between something that we call color ordered amplitudes. These are amplitudes that you use some trace basis to rewrite them, and these color amplitudes, they are gauge invariant. And then, but they're not actually independent. There are many of them connected by many of relations, such as Kleist-Kaif relations, etc. And these are relations that came from the fact that you're using this representation for your numerators. So this is an example of something that we call Bern-Carrasco-Johansson relations, the BCJ relations. And then, okay, this is good, but assume that I'm a very brave guy, then I want to calculate gravity amplitudes. So any one of those of you guys who try to calculate amplitudes using Feynman diagrams, Feynman rules, from the scratch, from the Einstein-Hilbert action, you will see that this is not a job for babies. They are actually hard to do. There are many, many, many terms. If you calculate, say, the simplest vertex involving just 3 gravitons, you will find 100 terms or more, or 200 terms, something like that, depending on the representation that you use. So not easy, not something that you want to do during your summer. But then, if you have this this representation, if you are sure that your Yang-Mills theory, your Yang-Mills amplitudes obey color kinematics duality, the idea is take the color factors away and replace them by the numerical factors, the n's, and then boom, you have a gravity amplitude. And then you can prove that this is actually a gravity amplitude by using usual methods. Of course, probably you're going to do some numerics in here, right? Assign some numbers and compare with this guy that you obtain using the double copy map. And then you find that this is the actual result. Of course, you use some sophisticated tools to prove this recursion relations, mathematical induction using recursion relations, etc. But you can prove that this is actual. This is actual gravity amplitude. And then these two numerators here, they don't need to obey color kinematics duality. Just one of them is enough for you to obtain. And from this here, right, you can rewrite your amplitudes in such a way that you prove that they obey the KLT relations at the quantum field theory level. So these are just examples of the KLT relations at the quantum field theory level. And well, I'm not going to have time to discuss this, but there are some more sophisticated tools that you can understand the KLT relations using something that we call intersection theory, and probably this will be useful to prove this at loop level, but this is another story. I can elaborate more for those who are interested in. Okay, so indeed, it seems that gravity equals gauge theory square, right? And then you can prove this, as I said, at any multiplicity level at true level, right? But there is a caveat here. The caveat is, in 4 dimensions, gluons have 2 degrees of freedom. So I'm saying that gluon square equals graviton, right? But as far as I know, 2 times 2 equals 4. And gravitons in 4 dimensions, they also have only 2 degrees of freedom. So you have 2 extra degrees of freedom here. From the string theory perspective, this is not a surprise, because if you take, let's say, bosonic string theory, the simplest example that you can imagine, and then you take alpha prime going to 0, calculate the effective field theory associated with this, and then the action that you find is not just the Einstein-Hilbert action, the Einstein-Hilbert Lagrangian, but you find some other ingredients, which we all know by now. What do those guys mean, right? You have an axion, you have a axion here, right? And then you have the dilaton. And then these are the 2 extra ingredients that come with the double copy. Even if you are in quantum field theory, not talking about string theory, you will find those extra ingredients. But of course, there are ways for you to eliminate those guys, right? Basically, you use state projectors. If you are calculating, say, those guys, right? So the amplitudes using KLT relations, the idea is to correlate the helicities of the gluons. So depending on the way that you correlate the helicities of the gluons, you find gravitons or the extra degrees of freedom, etc. But anyway, even though this is not quite true, there are ways for you to make it true, right? So by now we have a web of double copy constructible theories. So double copy constructible theories, I'm saying that gravity or gravity-like theories that you can imagine a theory that comes before it, and then you can use the double copy map in order to calculate the scattering amplitudes associated with this gravity-like theory. So there are many, many examples today, as you can see, and there are many other things here that even I can say for sure specific examples or the details or something, many things here, but it's something that grows. It's something that really grows. But these are examples at true level. So what about the loop level story? So schematically, the loop level story should look like this. But the challenging is to find numerators that obey this duality, right? Even in situations in which you would expect to find, say, for instance, n equals 4 super Yang-Mills theory, it's not obvious that you will have this. So it's not necessary. This does not necessarily mean that color kinematics duality is something that only works at true level. But the point is, if you use those tools, like the BCA form of the amplitudes, or if you use those tools using BCA form of the amplitudes, or if you impose color kinematics on a given ansatz to calculate the amplitudes, not necessarily you will find expressions that are more compact if you use more traditional methods. So this complicates the story. And another thing is that even if you use more modern tools such as on-shell recursion or generalized unitarity, those tools, they don't give you naturally numerators that naturally will obey color kinematics duality. So this is a very challenging process. Even though you have evidences at loop level, you don't have a schematic way to do this as you have at true level. So it's an open problem, right? But presumably those guys here, they managed to prove that you can use double copy to all loop orders, but they circumvent the idea to prove the double copy map. The idea is that, okay, they find a given, as they say, a global integrand basis. And this basis, you can expand any of your Feynman integrals and any order of perturbation theory, including planar and non-planar diagrams. And then the idea is to use a kind of a spinning set of cuts. By that, I mean cuts that are residues that you calculate, and each of these residues are going to address each one of those integrals on your basis. And then you have a map from this spanning set of cuts to this integral, to this basis of integrals. And then the spanning set of cuts is made of products of 3 amplitudes. And 3 amplitudes, you know that the double copy map works. So you use this map to the spanning set of cuts, and then use this map to obtain the global integrand basis. So you see, you are not using the double copy map to all loop orders. You're just using the double copy map to the 3-level amplitudes. But the 3-level amplitudes will be necessary to go to the global integrand basis. So it's a kind of a use of the double copy map to all loop orders without necessarily having to prove, right? But this is cool. This is really cool, and this will be really important to calculate higher loop orders of amplitudes concerning, as I will see in a given minute, the applications for gravitational wave physics, or more elaborated amplitudes in n equals 8 supergravity, which to this day we still don't know if this is a finite theory, if it has any given UV divergences. Maybe it is, maybe it has, but we don't know just yet. So, and this is, I'm going to skip, but there is another representation of the amplitudes, which we call CHY, and they have a kind of a double copy prescription, right? Not exactly, but the idea is that if you take these guys here that we call scattering equations, right, which is kind of an isomorphism between the number of kinematic invariants that you have in a given scattering process and the number of points on your sphere, right? So the solutions of this guy that we call scattering equations, they generically produce the amplitudes for gluons and for gravitons. So this is just, I can elaborate more, but I'm going to skip more details on this. But, well, this is also a very cool subject. Okay, so you can imagine, okay, if I can do the double copy, I can do the color kinematics duality at the level of the on-shell amplitudes. But what if I could do that at the level of the action, right? Or putting it in another way, may I use this idea, this reasoning, to map solutions of the classical equations? Well, there are examples that you can do, such as this one that I give in the slides. So in here, you can map Coulomb solutions to Schwarzschild solutions, Coulomb solutions in electromagnetism to Schwarzschild solutions in general relativity using this gauge, which is called the Kirchhoff gauge in Schwarzschild, for the Schwarzschild solution. But it's not systematic, and the reason is amplitudes. You can always go to a given representation, the color order representation, in which the amplitudes are gauge invariant, right? They are reparametrization invariant. But this is not quite true for classical solutions, right? So classical solutions are not generically gauge invariant or reparametrization invariant, right? And then you shouldn't expect that, right? You shouldn't expect this. So because of this, and another reason is, but mostly because of this, it's really hard to imagine that you have a systematic way to do the double copy between solutions. But it's incredible that in many examples you still have, and this is one cool example, of course. Everything that involves black holes, we are already happy, and this is an example that you have involving Schwarzschild solution, but the Kerr solution you also have this kind of classical double copy. Okay, so we are discussing tools, right, to calculate amplitudes and maybe to address UV divergences. But there is another story which is very important for us, which has to do with the infrared structure of the amplitudes. And this is really important, especially if you have long-range interactions. And this is basically what we are discussing here, right? Gravity, electromagnetism. And the fact that you have long-range interactions, the consequences for loop-level amplitudes is the generation of the so-called infrared divergences. And then you understand UV divergences by the process of renormalization or simply put, the uncertainty principle. But the infrared divergences are more serious, because for electromagnetism and gravity, these infrared divergences, they exponentiate. And then, of course, it's a generic divergence. So what you do, you regulate, as you do with UV divergences. And then at the end of the calculation, you want to take out this regularization parameter. But if you do that for gravity and electromagnetism, you will find that your amplitude vanishes, because generically speaking, it's like you have an exponential times a positive number and your leading order amplitude. And then if you take out your infrared regulator, this guy will vanish. So you have to come up with ways to deal with that, right? So this is really important. If you don't want to address more sophisticated tools, such as addressing the states using something like that we call Faref-Kulish methods, you can just take a very pragmatic picture in which the process of generating infrared divergences, which is associated when you are exchanging a massless particle and then you are going to the soft sector of this massless particle. That's where the infrared divergence is generated. You can also discuss about production of these massless particles as external states, soft brainstorm. And then you can prove that the both guys produces divergences which cancel each other. So that's what the textbook does for us, right? So you consider the most generic processes with a given number of external messengers, I mean massless particles, right? Gravitons or photons. And then all infrared divergences cancel, right? And then those guys came with many names, right? The infrared divergences, if you are exchanging massless particles. About the Brainstorm processes, they come also with the name as Weinberg derivated back in the 60s, and you call it the soft theorems. And the cool thing about this is that those guys are related to a topic that it came to be known in the 60s, parallel to all those understandings, right, of infrared divergences and soft theorems, but at that point was completely unrelated. And these are the symmetries associated with isolated systems in gravity, which by now we call asymptotic symmetries. So there is something that we call the infrared triangle, which is this. So the infrared triangle, they relate these three different topics. So soft theorems, as I was saying, right? Asymptotic symmetries, right? Which goes by the name of Bondy, Metzner, Vanderburg, Sachs group, or BMS group, right? Which has something to do with, well, isolated systems are, right? At infinity, your metric approaches the Minkowski metric. So you would expect that even if you have a situation in which you don't have any specific isometry, right? At infinity, you would recover Poincare, right? That's intuitively what you would expect. That's partially true. You obtain Poincare as well, but you also obtain an extra baggage, which now we call the BMS group, right? So the BMS group has to do with something that we call large gauge transformations in gravity, which has some peculiarities and some similarities with large gauge transformations that you can discuss in QCD, for example, but of a different nature, of course. And then those guys are related to something that we call the memory effect. And this is something that it's completely GR, right? It's one of those predictions of GR that we can probably will not be able to see this using our terrestrial gravitational wave interferometers, but probably the LISA or the space-based interferometers, such as LISA, will be able to probe these effects, because you need to go to very, 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 very low frequencies, which the LIGO cannot provide this for us. So if you put those guys together, you will see that you have a new way to try to understand scattering amplitudes. And then this has motivated this program that people call the celestial holography program, which is try to understand in this isolated system perspective the bulk physics from the perspective, from the knowledge of what happens at the future null infinity or at your celestial sphere, right? And this also has to do with the fact that the position of stars in the night sky, there is a relation between the position of the stars in the night sky and the way the inertial observers in the bulk observe those positions, right? So inertial observers are connected by Lorentz transformations. The night sky is basically the celestial sphere, and the Lorentz transformations at the celestial sphere are conformal transformations. So you kind of have a conformal field theory at the celestial sphere. I say kind of have because there are many issues that we still need to understand behind this program, but it's a very cool program, and it's basically it gives you a new, fresh perspective on scattering amplitudes, especially these amplitudes associated with isolated systems, and this is presumably very important for gravitational wave physics applications, right? Even though you don't need to go there, right? Usually people are trying to see another features from this. And then you can also have a double copy map. As Eduardo and Andrea put in this beautiful paper some years ago. And then this is just a sketch of how you do this, right? But you can do this at let's say at the celestial space, at the celestial representation. Basically, the celestial representation is a representation in which you're not using momentum states. You're using boosting states. You're using boosting states because they will describe the physics at the celestial sphere more properly than these guys, right? As I said, Lorentz transformations in the book are conformal transformations in the celestial sphere. Okay, so I have a couple of minutes, I think, or an hour or so, to address a little bit of these applications, right? So one of the most important applications here is associated with gravitational wave physics, right? So now you want to take all these ingredients that we have discussed so far and try to discuss observables that will be important for us as we are measuring gravitational wave stuff at LIGO, especially waveforms, right? So they use all those methods. They rely on two things that were at some years ago, they were kind of sacred. These two statements, right? So we would see one statement saying that gravity is fundamentally incompatible with quantum mechanics, and classical physics is always associated with your tree-level diagrams. So loop-level diagrams contain only quantum physics. And now we know that these two statements are simply wrong. There's nothing wrong when you combine gravity and quantum mechanics. Nothing. It's perfectly reasonable as soon as you assume, of course, that the GR is an effective field theory. So the perspective here is not the geometric one. The perspective here is to imagine that the gravity is just a quantum field theory of the massless spin-2 particle, the graviton. There is no problem. You would see that the associated quantum field theory as an effective field theory works out in the same way that you could imagine as with any regular effective field theory. So this is one statement that we reinterpreted nowadays. And the other statement, which is important for this program, is the fact that only tree-level diagrams are associated with classical physics. This is not true as well. If you have situations in which you have two or more massless particles inside your Feynman diagrams, so you are dealing with long-range interactions, those diagrams, those loop-level diagrams, will also have a part which is classical. So there is a part in your kinematic space or kinematic variables in which you have a clear separation of scales, in which classical physics will emerge. So that's the point. So even if you have a 5-loop diagram between, of course, we are talking about long-range interactions, gravity, for instance, and then you can be sure that you can extract classical physics from this. So you use basically these two tools, these two reasonings, to employ all my tools that I have discussed here to calculate classical observables from quantum amplitudes. So this is not something new, right? So and by the way, I'm not talking about this effective field theory, right? This goes by the name of non-relativistic GR, and this is a classical field theory, classical effective field theory in which you can calculate. This is a very suitable for binary systems, so you can use this to calculate waveforms or classical gravitational wave radiation. But this is classical from the scratch, right? So you're not calculating any quantum amplitude. This is completely classical, and then you can calculate a lot of things, especially something that we call gravitational polarizability for black holes, and then using the Kramers-Kronig relations, and those guys here, the love numbers for black holes which are vanishing. You can, I can elaborate more on this, but you can derivate some rules, gravitational some rules for this. But this is not what I mean, right? This has some time, many years, 20-ish decades, from the works of Goldberg, Rothstein, Porto, and then after that, a little bit after that, Fofa, Storani, and then I'm not going. This is not the thing that I'm mentioning this, but what I'm mentioning is this, right? This paper by Iwasaki from the beginning of 70s, but here he was just considering the lowest order of the Newtonian potential, which is given by the tree-level diagrams, but also this paper, which is more recently. And this paper gives us a more general recipe, more, let's say, broad recipe, for you to see how classical general relativity can be derived from scattering amplitudes. Well, the story goes as follows, right? The folklore. The folklore was that in a given paper, Thibault Damour has invoked folks from the scattering amplitude community to help him understand the post-Newtonian and post-Minkowskian expressions. Of course, this was not just this story, but I'm shortening this way. But he even wrote in the paper, right? You'd be nice to see the scattering amplitude guys to address these problems, etc., etc. And then those groups put their efforts together, and then those papers came out almost simultaneously, and they happen to address the same thing, but they use kind of a different perspective to do the calculation, right? This is more modern, right? This there's nothing wrong about the calculation that they do, but they now understand that there are better ways for you to understand this. But then, apart from this, those two papers, right, and the generalizations that came from them, they gave the general recipe of how you can extract the classical physics from the quantum amplitudes at any given order in your perturbation theory. So, of course, we will be especially interested in black holes. And as funny as it may seem, black holes are actually the simplest objects that we can consider. And this is because the no-hair theorem, the kinematic counterpart of the no-hair theorem, is the fact that at a given order of your perturbation theory, black holes behave as particles. So you can just use a point particle Lagrangian to describe, add up to a given order of your perturbation theory, the dynamics of, say, a binary of two black holes, right? And this is very interesting, right? Because it facilitates the computations, because you can use all of your tools to discuss about dynamics of two, let's say, giant black holes orbiting each other. So up to some order of your perturbation theory, you can study them, right? So this is the phase that we are interested in using those methods, the spiral phase, right? So I'm taking the example of the merger processes of two black holes, right? But at the merger, you cannot use these analytic tools. You have to use, or semi-analytical tools. You have to use the numerical relativity. Of course, you can use numerical relativity for everything, but it's really costly. It costs too much. It's computationally costly. So the best idea is to put different methods together and see how they match. And it's nowadays one of the things that people do is to see how numerical relativity results match with the semi-analytical results in the spiral phase. And then you see that it's impressive. It's impressive, the matching, right? So the analytic tools are really, really important, cool, and they facilitated the constructions here. So this is just a generic a picture of what we are doing, right? So you will start with your physics. So you want to describe this, right? So you use a given theory, for instance, the point particle effective field theory given by Goldberg-Rothstein, or the way that we are describing. So so you are describing, for instance, those processes, right? So these guys here are describing, let's say there's just massive scalar fields. So we're describing two massive Schwarzschild black holes. And during this scattering process, they are exchanging many gravitons here. So there is a recipe to extract from a given diagram the classical part. And then the classical part, you can match with this non-relativistic effective field theory, right? You take this potential, and then you expand this in powers of G. And then you have this generic coefficients. And these coefficients are calculated once you match with the calculation that you do. So that's the generic picture. Right? So basically, if you want to calculate, for instance, amplitudes to describe scattering processes, or collision or merger process involving curved black holes, these are the amplitudes that you will use in the classical limit. Right? Classical here means that you're going to take the quantum spin, the infinite quantum spin limit, right? You can prove that this gives you the classical counterpart of your amplitude. So, so you can prove that this equals this, right? This you can calculate from classical, such as papers by Justin, etc. And then from the quantum counterpart, you can see that you have a perfect matching once you take this and use this gauge condition, which we call spin supplementary condition. Which I'm not going to be able to address this, but I can elaborate more. So this is just to give an example of things that you can calculate using the other formulas that I mentioned. This formalism here. Oops. This formalism here, right? Which we call KMOC. Kozoer, maybe O'Connell. KMOC. So you can calculate the impulse between scattering of two generic spinning massive particles. So you can do this for electromagnetism. So you see, it's a very contrived formula, a very complicated one, but the calculation itself is not really hard. It's not really hard, even though it looks hard, but it's not really hard. And then from the impulse, you can calculate in scattering angles, right? And then it's difficult to see, but there is a double copy map between here, because inside here, there are amplitudes. And then you can use the double copy map to calculate the gravity amplitudes from the knowledge of electromagnetic amplitudes. And then you can just, there are certain formulas to calculate those guys, and then you generate those guys, right, to do this, right? So you find another formula which has some similarities to the other one. It's difficult to see because I have to pass fast, but I can elaborate more. But there are terms here that were associated with each other by using the double copy map. And then you can do this as well for something that we call, I'm going to pass this because I won't have time to do this. But you can use this as well to calculate amplitudes for something that we call the spin kick, right? But all those amplitudes, all those observables will depend on something. Whoops. Whoops. It doesn't work. This is working, but it's not working. No. Maybe it has some time, no? So it's warning me that I passed my time. So yeah, let me turn it off. It's funny because the pointer is still working, but it's not passing. May I see here? Oh, I can pass here. All right. So those objects, you see, I put here up to order of a given ring radius. And this is because to calculate this part of the impulse, you need an amplitude, a Compton amplitude. And the Compton amplitude for a genetic spinning massive particle is not really well understood because it generates spurious poles. I'm calling spurious poles because at tree level, we know that the only analytic structure of rational functions are simple poles. And the simple poles must describe the exchange of particles, physical particles. So if you have a pole which is not associated whatsoever with the exchange of a physical particle, you call it a spurious pole. In principle, it's not a problem if you have a spurious pole. There are representations of the amplitudes in which you would have generic spurious poles. The problem is that if those poles has non-vanishing residues, which is this case. So this thing generates unphysical parts for your description of scattering. So you have to eliminate this. The genetic idea is to add contact terms in which they are tailored to cancel the residues associated with this unphysical poles. So that's the idea. But then this I'm going to skip. But then the idea is that if you add these contact terms, the unitarity method that you can use or recursion relations to calculate those amplitudes, they are completely blind to the nature of this contact terms. So these contact terms are ambiguous. So you have to find a way, a physical way, to eliminate these ambiguities from those contact terms. So this is one of the ideas, right? Those guys, they saw that at a given order in the expansion of the spins at the classical level, the amplitudes have this sort of symmetry that we call the shift symmetry, spin shift symmetry. And then you can use this symmetry as one of the ingredients to fix this contact terms. So you eliminate, so in principle, you eliminate this this problem of these ambiguities coming from these contact terms. By now, we know that this is just an approximate symmetry. So this is not something that you would expect to all orders in the classical spins, in an expansion of the classical spins, or the multipolar expansion in your classical amplitude. Another solution is to just use black hole perturbation theory. So you use black hole perturbation theory to correct these ambiguities. And this is more physical and presumably the most correct procedure to do that, right? This is also another solution for you to do this, which is consider a given higher spin gauge theory or higher spin theory coupled with gravity. And then you eliminate the ambiguities of the high spin theory using a general recipe, which follows from the physical expectations that you would this theory can provide to match the predictions from black hole perturbation theory. So in principle, this is also important, and this is also very useful to understand this. And then you can prove also that those results match those results here, right? But those then together, they do not match the first solution, right? As I said, the spin shift symmetry is good up to a given order in your multiple expansion at the classical level, not at all orders. So it's not a surprise that B and C do not match with the predictions of A, but B and C at a given, to a certain extent, they match each other. Well, one thing that you can think of, well, we do have a theory that deals well with this tau or higher spin massive particles, which is string theory. So you can try to imagine whether string theory could be helpful here in order to organize this amplitude. And to a certain extent, it is, right? You can do the recipe to calculate the Compton amplitude, which I didn't mention here, but the problem is the Compton amplitude with opposite helicities, right? And then, well, on one hand, this amplitude does not display any more of the spurious poles, which is expected, right? You are calculating something that makes sense from a theory that we know that is mathematically consistent, right? On the other hand, it doesn't match the results of black hole perturbation theory to all orders in the expansion of spins, but up to a given order, right? Up to a quartic order. You can, it's actually quartic, not quadratic, but quadratic in quantum spin, but quartic at the classical spin. So it's quartic instead of quadratic, it's quartic. But maybe there is a way to cure this, because to do this computation, you are using just the scattering at the leading radial trajectory. So maybe if you consider also subleading radial trajectories on your computation from the string theory, maybe you can make this, you can construct an amplitude to match the higher spin amplitude or the predictions coming from the black hole perturbation theory. This is to-do list. Let's see. And as was mentioned, this is also something that you can calculate using this King-Mark formulas, which we call the spin kick, or the I mentioned the linear impulse, but you also have the angular impulse, the variation of the intrinsic angular moment of particles in a given scattering experiment. So these are the two objects that you can calculate, the formula, and these A's here, right? These are the amplitudes. So these are basically the same amplitudes that you would use in the impulse formula, but now you can correct with a given Compton amplitude which is completed without the spurious poles. One coming from the string theory, or the other one coming from the higher spin theory by Herring and others. Oh, this is also, let's just briefly mention this. This is something that we've been working on. This will be really cool once you are calculating waveforms, because there was let's say, a caveat when you use this formalism, the K-Mark, to calculate waveforms in the non-spinning case. The caveat is the following. One of the caveats, right? When you calculate this, the waveform, using the recipe coming from the K-Mark formalism, the result does not match if you do a computation similar to what Thibault-Darmoud did using just a classical formalism. And the reason is the two frames that they used were different. The frame that Darmoud used is a frame that we call intrinsic frame. This intrinsic frame makes the radiated angular momentum to be present at orders lower in G than you would expect coming from the amplitude-based perspective. And the frame that those guys used was the so-called canonical frame. So there is a way for you to relate those frames using asymptotic symmetries. And eventually, the thing that you the thing that you use to relate this is something that we call the transformation that you use to relate those frames is something that we call supertranslation, which are angle-dependent translations at the celestial sphere. So you prove that not only this, there are also ingredients as well, but this was one of the most important ingredients. After you understand how to relate those frames, you find a perfect match between the calculations. But this was for no spinning case. So we were working now on a situation in which you consider the spinning case. And this is more important because now you can calculate spinning waveforms, curved black holes. And then presumably this will also be important when you calculate something that you call higher spin charges using amplitude techniques. So this is in the near future perspective to do. Okay, so let me finish my talk by saying a little bit of words of higher derivative theories, right? So this is a higher derivative gauge theory, which has this Lagrangian, and then the importance of this higher derivative theory is that it can be used through the double copy to calculate amplitudes in a given conformal supergravity theory that was found by Nathan and Ed Witten in their famous paper in which they're studying the multi-trace sector of the Twistle string. And then presumably this theory, this df square theory, is important to address those amplitudes using the double copy map. So this is an application important for this, right? And then you can generalize to the super case. So you can consider the super df square theory in order also to try to address this no minimum n equals 4 conformal supergravity as, let me just be more specific, as studied by papers by Ferrari and Lust some years ago. So presumably using a double copy map from the super df square theory, you'll be able to calculate the amplitudes on those theories. But one of my motivations to do this was quadratic gravity. And despite some negative comments concerning this theory, it's still a viable option to address the quantization of gravitational interactions. I can elaborate this more, but I won't have time to do this. But this was one of my motivations to address the other problem, right? But if you want to stay only on quadratic gravity, you can do this, right? And these are some recent results concerning this, but I can elaborate more on this afterwards. But the idea is that you can use also those double copy maps to calculate these amplitudes. So you imagine, only if you have this Einstein-Hilbert term in the action, it's really hard to do the computation, right? Imagine if you, up to this, on the top of this, you also add a high derivative term. So it's really mess if you want to calculate amplitudes using traditional methods. So it's really fortunate that we have a double copy prescription to do these computations, right? And these are amplitudes that you can calculate. I'm going to skip a little bit of this, but again, I can elaborate more on any curiosities. And then, okay, then you can use also to calculate something that we call causality violation. This is the, if you want, the caveat associated with this type of higher derivative theories. And then you find this, you see you have a negative term in the time delay. And then, again, I can elaborate more on this, but you can use amplitude methods to address this, right? Okay, guys, so this is just a list of things that we are doing now and the near perspective topics that we're planning to address using these applications. And then let me just call attention to the the QCD Meets Gravity conference and school that we expect to have now next month. I hope to see some of you guys in there. Unfortunately, the deadline has closed, but anyway, there will be some broadcasts of the speakers here, of the talks, and then I know I talked too much, so let me finish here, and I'm ready to take questions. Thank you very much.
Okay, thanks, Gabriel. Let's open maybe for one or two questions. since it's already lunchtime.
Maybe I'll ask.
I asked before if you guys were hungry, and you haven't said anything.
So maybe I hope it's a quick question. So is there any relation between double copy and the first order formulation of gravity?
In the first, you mean the Palatini action?
For example.
Well, there.
So in some sense that first order formalism is the square root of the second order.
If by that you mean at the level of the action, I'm not sure. It might be, but at the level of the amplitudes, right? Let's say I want to calculate an amplitude through the Palatini action, right? Through the Palatini. You should be, and I think I've seen at least a paper on this, but I might be wrong because it's a different formulation, right? But in principle, you should this. But the catch is, what is the Young-Mills theory that you are using, right? If you come up with the correct Young-Mills theory, then not a problem. You can use this.
Okay, so I suggest we take the discussion for lunch. And Gabriel, thanks again.
Thank you.